willing to join also next year. And then let's hand over to Jörn to his talk about muscles.
Thank you.
Thank you, Martin. So just so I fully make sure everything is, you want me now to present and not our student group, is that right?
Yes, that's right, because I think in the program there will be a presentation of the student group.
Yeah. I just want to make sure I don't spoil it again.
Oh, no.
So let me see, where is my... Where's my PowerPoint? Here we go. So, thank you, Martin, for having me and letting me speak about something that's really on my mind since about 2 years. And I put it to a question that, it's about muscle stiffness, and I put it to a question which, of course, looks really stupid. Should we be measuring muscle stiffness, or is it the same as muscle force? Force comes in Newton, stiffness comes in Newton meters per radians, or in Newton per meter. So only a simpleton medical doctor like me could probably ask that question. Forces don't smell, we can't see them. So the only way we can talk about them is either looking at what they accelerate. And I have put this little symbol of an actuator here, which we put in mechanical diagrams. Or the other way where we can infer upon forces is in elastostatics, where forces can actually elicit deformation of solid or other materials. And then we are speaking of the spring constant, which is given as the change in force. The change in force is given as the spring constant times the change in stiffness, the change in position, and then the K is the stiffness. Elastic springs are typically linear springs, and the question arises, what if you put them in parallel, or what if you put them in series? And it's in a way, it's a bit similar then to the actuators. If you put two actuators, two engines in parallel, then of course their force and power output double. And the same is true for two springs. If you take two springs in parallel and you try to compress them, you need twice the amount of force, provided the two springs are identical in their properties. Now, if you put them in series, then something really awkward happens. With the actuators, the velocity doubles and the force stays the same. But in the arrangement of springs, really, the stiffness is halved by 2. Yeah. So that tells us that once we, our brain is not really made to talk about forces. And I think it's even less made to talk about stiffnesses. So it's getting a bit more complicated. So we also have in the field of well-established muscle physiology models that talk about stiffnesses. The classical one is A.V. Hill's paper about the heat of shortening. And if you really read it, I must admit, I don't understand all the details of it, but I've asked a student of theoretical physics to read it. And she tells me that the so-called Hill-type model, which is always, referenced as the 1938 reference of A.V. Hill, does not really include it. So one of these long strains of citations in the scientific literature, and what the Hill-type model suggests is that in order for a muscle to really work, you need the contractile element, that's the actuator, and then you need a series elastic element and a parallel elastic element. So the parallel elastic element is needed, it was postulated by Hill, so that after a contraction, the muscle is lengthened again. Okay, and so you could really look at this arrangement then as the actuator just modulating and mediating, negotiating the stiffnesses of these two elements. A more complicated, well-known muscle model is Zayak's muscle model. So he places elastic elements at the ends of the muscle, the aponeurosis, extensions of the tendon into the muscle. And then, of course, you also have parallel elastic elements and serial elastic elements here within the muscle fascicle. So from this, we must expect that stiffnesses must be considered whenever you talk about muscles. And it's getting even more complicated when we try to translate from the muscle stiffness onto the stiffness of a geometrical structure such as a leg. And I'm really happy to present these diagrams here, which I got from a recent paper in the New Steel Construction magazine. It's about some bridge girders or something that they and I really found it interesting that the mechanical elements, they're almost the same as the human legs. So I've been using sketches like this in a few talks. And the important thing here is, it's straightforward to say what is joint stiffness. You basically have to multiply the stiffness of the muscle with the lever arm. But then when you talk about the leg stiffness, you have to consider that with the knee flexion angle, the length of the spring is reduced. And at the same time, the point of force attack here attaches at a larger lever. And so the equation then becomes already a bit more complicated, and many scientists have actually directly translated this muscle stiffness into the leg stiffness, and I think this is simply wrong. Why does muscle and leg stiffness matter? It's well known in athletics that you need a good track. So the track needs to be somewhat compliant. And the father of all this research was Tom McMahon. I didn't find a picture. I know I have one in my office, but I couldn't find it, for the preparation of this talk. He was a real genius, and one of his best papers really is the one about Groucho running. And the young people may not know Groucho Marx. If you don't know him, go on YouTube, try to find him. He's really funny and he's really serious. It's really, and Tom McMahon devoted this paper to Groucho, and the question he was asking is, what happens really when you do the Groucho running? So when Groucho Marx in the movies, in the films, ran, he was always running with the center of mass showing almost no displacement. So basically, it's a race walking style in running, and he did the biomechanics of this. And there are a few remarkable things in addition to this finding, that if you reduce the stiffness of the ground that you're running on, you can actually you can increase the time of ground contact. And the time of ground contact in athletics is really important because that's the time where you can propel. That's the time where you can accumulate running speed. So, fast tracks are fast because they are more compliant than the environments that we normally have, the grounds that we normally have. And then another important finding of that paper is that in order to run, at a certain speed, you have to provide stiffness, because at each step, the leg will shorten and lengthen again. And the stiffness required for a given speed grows with the square of the running speed. So stiffness is really a limiting factor. And flexing your knee more during running is an effective way of reducing the overall spring stiffness. And what's not mentioned in the paper, but what's probably known to most of the audience here, is that, of course, stiffness in a spring mass system is also a determinant of the resonant frequency. And when you're running, you need to have a certain resonant frequency in order for the bouncing periods matching really the stride length. So that's really important. I think that stiffness in the muscles will also turn out to be very, very important in the medical field. So you see here that in children with cerebral palsy, in most cases, a primary disorder of the brain, and maybe in 10 to 20% of the cases, a primary disorder of the spinal cord, but always of the central nervous system, the muscle between the age of 5 and 10 years after birth develops a phenotype that is characterized by a very high proportion of type 1 fibers and a very stark enrichment in connective tissue. So that's one, and you may know that these children with cerebral palsy, they suffer from spasticity, and they really have stiff muscles, and evidence suggests that this is very important also for their gait disorders. And then another condition where, and I will show in the next slide that here in this cerebral palsy condition, the stiffness of the muscles is increased. In the Ehlers-Danlos syndrome, we have hyperflexibility of all kinds of connective tissues. And I suspect that the muscles also experience problems with these. We are running a study with these patients right now where we look at the internal muscle dynamics, and we see some really surprising findings that I will be able to talk about in a year or so. So coming back to the cerebral palsy, it's been demonstrated here that if you take out muscle fibers from a muscle in these patients, and you just look at the single fibers without the connective tissue, they're not different from a control group. Yeah, in two different muscles, and in particular, the gracilis is a muscle that changes its phenotype in cerebral palsy. Then, when the researchers here took out fiber bundles containing the connective tissue, they could demonstrate that the passive stiffness of the muscle was increased, and that this limited the range of motion and the overall behavior. So far, literature has focused, if there was a focus at all, on the passive stiffness of the muscles. And several papers show that the passive stiffness of the muscle has nothing to do with changes in the specific tension of the muscle or the stresses, and also not with the force output. So the question really arises, what is happening, what is the importance of active stiffness, not stiffness when the muscle is relaxed. This is functionally probably not important. It can maybe predict
So Jörn, you're off. I think we can hear you. Let's hope that he's able to reconnect. So I expect him to be back in a minute or so, but I will double check. So I just called him, so he had an unexpected problem. He's going to be back in a minute or so. Yeah. So let's wait and see if we still have time, the buffer. So that should not be a problem.
Sorry, I'm back now.
Okay.
Stupid mistake. I just ran out of battery power. Apologies. I think I was here. So talking about active muscle stiffness, and this can actually be measured in a so-called.
Share your screen.
Yeah.
If we may see your slides.
Yes. Okay, so you can see this quick release here. The subject is asked to tense the muscles, and then there's a quick release, and from the acceleration and the change in acceleration initially and the change in position, you can actually calculate the stiffness. And it has been shown after spaceflight that for the same torque exerted here around the ankle, the stiffness increases. So deconditioned muscles seem to be becoming stiffer than well-trained muscles. Now, it's not easy for most people to have such complicated dynamometers as we have them in the lab. So an easy field test that I feel can be used really to measure stiffness in a broader population could be done probably on a simple platform. And Martin, that's the essence basically also of our joint project in the summer, maybe even with accelerometry. So we are currently, or traditionally, we are doing two different tests. One is a counter movement jump, and I've been demonstrating results from this test over the past years. Also at this meeting, it's a very, very accurate measurement of muscle power with regards to age effects, with regards to training effects, with regards to athletic specializations. So sprinters at young years have very high power. And we found out in the last year that we can also explain most of the age-related changes with body composition. So sarcopenia seems to be really the reason why the counter movement performance declines with age. So the power here is a very good measure of muscle, I think. Then the one-leg hopping we've been using in order to look at the maximal, let's say, force acceptance of the body. And we have a paper in preparation where we show that, you know, equally powerful, the age-related reduction in the peak force exerted during this test declines with age, and we can largely explain it with changes in body composition. But it's a different capacity of the muscle than the power. So the two really help us to describe two different aspects of muscle function. Now, the stiffness, I have a hunch, can be nicely measured with the two-leg hopping. I won't go into many details, but I can show some results from a previous study that we did. So this was a study with young and old sprint or jump trained athletes versus sporting active people. And when we plot the power versus the force, you see there's quite a wide of scatter. There is some kind of relation here. So again, the message is that power in the counter movement jump and the force in the one-leg hopping, they measure different aspects of muscle function really. Now, when we look at stiffness, I have to admit this was in that study still done with the one-leg hopping. So we measured one-leg stiffness. You see that in this group, in all but one group, three groups out of 4, you see some kind of dependency. So there's collinearity between the stiffness and the force. But in the old non-physically active people, you have a wide scatter here on the stiffness scale and very little variation on the force scale. So I think that in this group of deconditioned people, it can be really important to measure stiffness. And stiffness, increased stiffness in combination with reduced power and reduced force acceptance capability of the system could be an important hallmark of inability really to locomote. So that's my idea. And you can see also from this study, power declines with age, and of course athletes trained in sprint running and in jumping, they have higher power than non-physically active people, both at young age as well as at old age. With the force, not much of a difference between these groups, but the old, not physically active people, they are way lower than the other three groups, and they display larger variation within the group. And then when you look at the stiffness, actually, qualitatively comparable to the force, but the change is in the opposite direction. So reduced force, but increased stiffness. So I really think that looking at stiffness is important. First results from that study suggest that the differences that we see in stiffness may not be due to changes in the muscle, because we have also obtained muscle biopsies. Connective tissue is not accumulated in this group. So it may be to do more with the configuration of the leg geometry than really with the muscle. And so, Martin, this is just the invitation again that, despite all the craziness around us, we are confident to go to Finland in the summer and really look at the links between the functional capacity, and the aim is really to assess power, force acceptance, and stiffness, and then look at performance prediction in the athletes to really know whether, which of the measurements that we take in the muscle is important. Now we close with my normal slide with some amendments. So I'm really happy to see that now in Europe we are coming towards an understanding of a merged or a collaborative defense policy. I think given the craziness of decision makers in Russia at this stage, only focusing on military options may be very dangerous. I think we need civilian measures that are at least as powerful as any military measure. Otherwise, we will come to a deadly spiral of craziness. And I think we need a European understanding of how we jointly deal with our energy. And I think an appeal to all of us, not only on a personal level, but also on a professional level, we absolutely need to cut our dependency on oil and gas. And in my capabilities, what I've determined to do is look at how we can use our knowledge about human physiology in order to improve our heating system so that we can reduce energy dependency while still living in comfortable homes. And with this, I'm finished with my talk and happy to take questions. Apologies again for the mishap.
Okay, so thanks a lot, Jörn, for this talk, including the extension at the end where you were linked to actual politics. So maybe one comment from my side about this project in Finland. I also very much hope that it's going to work. I actually would hope that, as it happens to be the case, that young students and researchers will join you. And I think there are 3 of them from previous lectures that will join you in this effort, and we will have the equipment ready. And I think the interesting part could be to be able to have also here data, big data that can be used for exploration with different student teams, because there is the possibility to come up with new or improved outcome measures for people in the aging society, sarcopenia and whatnot, to have a combination of real world measures like walking speed or then jumping test stuff. So that's really very helpful. Okay, so we have a little time for questions. So let me go through the list to see if we have anyone who has a question or a comment. Okay, if this is not the case, I mean, you've given me a very nice way to find the bridge to the next talk, because one way is to have improved